In this video, I will introduce you to something called the antiderivative. Here's the definition. A function capital F of x is an antiderivative of f of x on an interval if the derivative equals f of x for all x in that interval. The key to understanding antiderivative is right here. The derivative of an antiderivative gives you the original function back again. Let me illustrate what I mean with an example. Find two antiderivatives of f of x equals 3x squared. To find an antiderivative, you have to answer the question, the derivative of what function equals f of x? So, what function will give me 3x squared if I take the derivative of it? Imagine the power rule. When you do the power rule, the exponent comes down in the front. So I see this 3 in the front. So maybe my antiderivative will be x to the third power. Let's check. So this is our guess. Often we will find an antiderivative by making a guess and then making some modifications. So let's check this answer. If this is truly an antiderivative, if I take the derivative, I should get 3x squared back again. So let's take the derivative. Capital F prime of x. So like I said, we would do the power rule, and the 3 will come in front. Then we reduce the power by 1, and we get x squared. So take a look. We got the original function back again. That makes this an antiderivative. However, the problem says find two antiderivatives of f of x equals 3x squared. Well, I already found the one that works. What else could there be? I don't know. Let's think about it for a second. So f of x, is there a way I could start with the same thing? Because I kind of need this in order to get 3x squared. Well, what if I just added something on the end? Maybe, let's say I put a plus 5 on the end. Would this still work? Let's check. Let's do capital F prime. Let's take the derivative and see if it still gives us 3x squared. Well, the power rule happens, and we have 3x squared. Then we get to the constant. Oh, okay, I see. If we take the derivative of a constant, that's 0. So it still gives us the exact same thing even when we have an extra constant on the end. So very quickly you can see that it didn't matter what constant we added on the end. Any constant would have worked. So any function of the form capital F of x equals x to the third power plus c will be an antiderivative of the original function 3x squared. So this expression will represent the entire family of antiderivatives. So we just saw that you can represent the entire family of antiderivatives of a function by adding a constant to a known antiderivative. So in example 2, let's find the entire family of antiderivatives of f of x equals 2x. To find the antiderivative of 2x, we have to answer the question, the derivative of what function equals 2x? Think about the power rule. If we take the derivative, the exponent ends up in the front. So because I see this 2 in the front, I'm expecting that my antiderivative must have an exponent of 2. So I'm going to start with a guess of x squared. Since we want to find the entire family of antiderivatives, let's go ahead and add a constant on the end of this. Let's check what we have so far and see if it works. If this is the antiderivative of 2x, if I take the derivative of this, it should give me 2x. So let's take a look. let's take the derivative and see what we get. So, because of the power rule, the 2 will go in the front, and then we reduce the exponent by 1, so it's just x, and then the derivative of a constant is 0, so we write nothing. There it is. So that means capital F of x equals x squared plus c is the general antiderivative of 2x. So here's some vocabulary that we must begin to get comfortable with. The constant c is called the constant of integration. The family of functions represented by capital F of x is the general antiderivative of f of x. And capital F of x equals x squared plus c is the general solution of the differential equation f prime of x equals 2x. So I'm mentioning the concept of a differential equation. A differential equation in x and y is an equation that involves x, y, and derivatives of y. So focus on the derivative. For example, if I have an equation like this, y prime equals 3x, this is a differential equation because of the y prime. Or if I have y prime equals x squared plus 1, this is also a differential equation because of the y prime. So solving a differential equation will involve getting rid of the prime and getting y by itself. Let's start off with a really simple differential equation. Find the general solution to the differential equation y prime equals 2. Solving this simple differential equation means getting y by itself. So in order to do that, we once again are asking ourselves the question, the derivative of what function will equal 2? Notice this is the same question that we ask ourselves when we are trying to find the antiderivative of a function. So solving a differential equation and finding the antiderivative are the same thing. So in this case, it's pretty simple, that it won't take too much thought. The derivative of what function equals 2? Well, of course, that would be 2x. If we take the derivative of 2x, that's going to give us 2. We just need to add the constant of integration so we have the general solution to this differential equation. This function was so simple that we don't really need to check the answer, but let's follow good habits and go through those motions anyway. So if this is the solution to the differential equation, then y prime should equal 2. So just look back at it one more time. If we take the derivative of this, of course, the derivative of 2x is 2. And the derivative of a constant is 0, so we just have y prime equals 2, and that's what we wanted. Notice one more time that this is the antiderivative of the function 2. Now it's time for me to introduce you to indefinite integral notation. So far, I've been using this word antiderivative over and over again. And hopefully you're getting comfortable with what antiderivative means. But there's another word that means the same thing, and that word is integration. We have a symbol. This is the integral symbol that looks sort of like an elongated S. And this symbol means find the antiderivative of the function. So look at this notation, and I've got the vocabulary color coordinated for you. The function that you're finding the antiderivative of is called the integrand. We've got this dx on the end that's called the variable of integration. And of course, the result that we get is the antiderivative of f of x that we're looking for. And we've already talked about the c on the end is the constant of integration that gives us the entire family of antiderivatives. So you're going to be seeing equations in this form a lot. So let's get comfortable with how we will read this. There are three ways that this can be read. you can read this the antiderivative of f with respect to x, or sometimes you'll hear the integral of f with respect to x, but more informally you might hear the integral of f of x dx. All of these mean find the antiderivative. We've learned that finding the antiderivative means answering the question, the derivative of what function equals f of x. So that question is really captured by this little equation right here. See if you can match it up. The derivative of what function is equal to f of x. That's the antiderivative. Let's apply this new notation to an antiderivative that we found earlier in the video. So we found the antiderivative of the function 3x squared. So now instead of saying antiderivative, I can say the integral of 3x squared dx is, but I'm still just finding the antiderivative. And we decided that the antiderivative was x to the third power plus c. So this meant the following. The derivative of x to the third power plus c is equal to 3x squared. So these two equations are two different ways of expressing the exact same thing. So you can go back and forth between the blue form and the yellow form anytime. To be clear, indefinite integral and antiderivative are synonyms, and the process of finding the antiderivative is called integration. Also, let me emphasize that the operations of derivative and antiderivative are inverses, in case you can't tell from the names. So if I take the derivative of an integral, the two cancel each other out, and we're just left with the inner function. Or if I take the integral of a derivative, again, the integral and the derivative cancel each other out, and we are again just left with the inner function. For example, if I have the derivative of the integral of 3x squared dx, that's just going to be 3x squared, because the derivative and the integral will cancel each other out. Similarly, if I have the integral of d dx of x to the third power dx, I'm just going to get x to the third power. I do have to add on the constant of integration. But again, essentially, the derivative and the integral cancel each other out. Example 4. Find a rule for the indefinite integral of x to the n power. Let's practice using our notation. So the integral of x to the n power dx. So again, we're still just finding the antiderivative. That means we are asking ourselves the question, the derivative of what function equals x to the n power? So think about the power rule. We know when we take the derivative, the power decreases by 1. So when we make our initial guess, it might be a good idea to start with a function that has an extra 1 for an exponent. That way, when we do the power rule and decrease this by 1, we will be left with x to the n power. So maybe this would be a good guess. I'll go ahead and put my constant of integration. So let's check and see how we did. If this is truly the antiderivative, that means if I take the derivative of this, I will get x to the n power back again. So if we apply the power rule, the n plus 1 is going to come to the front. So I'm going to wind up with n plus 1 out in the front. I will decrease this by 1, so I'm going to end up with x to the n power. And of course, the derivative of the constant is 0, so that goes away. So this is close. I'm getting the x to the n power that I wanted, but I have this extra n plus 1 sitting here in the front that's messing everything up. So how can I modify my initial guess to compensate for this extra n plus 1? I have an idea. I want to cancel out this n plus 1. So imagine that we put an extra n plus 1 in the denominator. Okay, let's check it again and see what happens. So let's go ahead and take the derivative and see if somehow we're going to get x to the n power. So as I take the derivative, again, I'm going to do the power rule. So this n plus 1 exponent is going to come to the front. So I'm going to have n plus 1 in the front. And then I decrease the exponent by 1. So that's going to give me x to the n power. However, because I have this extra n plus 1 in the denominator, that's still there. So now that extra n plus 1 does cancel out the n plus 1 that's in the front. So that is in fact going to leave me with x to the n power. So this is the antiderivative. One thing you are going to have to face about learning calculus is that calculus involves a lot of memorization. So in a minute, I'm going to give you a rather long list of integration formulas that you're just going to straight up have to memorize. But one of those is what we just sort of proved. We discovered it. So the integral of x to the n power dx, we just found that that was x to the n plus 1 power over n plus 1, where of course n cannot equal negative 1 because you can't divide by 0. But we just figured this out. But now we're going to add this to a list of other integration formulas that from now on we're just going to simply memorize. So yes, I'm going to give you this long list of basic integration formulas that I'm going to ask you to memorize. But I did want us to figure out a couple of them sort of by hand so you can have an appreciation for where these rules come from. So let's try to discover one more. Find a rule for the antiderivative of sine x. So again, using our notation, we could write it this way: the integral of sine x dx. So you should be asking yourself, the derivative of what function equals sine x? We know that sine and cosine are very closely related when it comes to derivatives. So let's make our first guess. F of x equals cosine x plus c. Let's go ahead and add on the constant of integration. So let's go check it and see how close we came. If we take the derivative, we've memorized that the derivative of cosine is actually negative sine x. So that's really close to what we wanted, but we want just plain old sine x, not negative sine x. So again, how can we modify this? How can we modify our initial guess to compensate for this extra negative sign? How about if we put an extra negative sign in the front of this? Will that solve the problem? Let's do our check again. So when we take the derivative of a function that has a negative sign in front, we're allowed to leave the negative sign out in the front and then go ahead and take the derivative of the remaining function. Okay, now what happens? So we have the negative sign out front, but the derivative of cosine is negative sine x. Of course, the derivative of the constant is 0, so that's gone and dealt with. But because we included the extra negative sign in the front, these negatives cancel each other out. A negative times a negative is positive, and we end up with regular old sine x, which is exactly what we wanted. That means this is the antiderivative. And here it is right on the list of basic rules of integration. The integral of sine x dx is negative cosine x plus c. In the next video, I will give you the entire list of basic integration formulas. I'll give you a chance to pause your screen and write them all down, and then we'll do some practice. See you on the next video.